Tonight, we're going to answer a question that seems straightforward, but will shake everything you think you know about our cosmic home: the true scale of the Milky Way. And here's the twist that's going to change your perspective forever. The answer depends entirely on what you're comparing it to. Because the Milky Way is genuinely one of the largest galaxies in the entire universe, sitting in the top 5% by size, containing hundreds of billions of stars across 100,000 light-years of space. But it's also a tiny speck when you zoom out to cosmic scales, barely visible against the vast structures that span hundreds of millions of light-years. By the end of tonight, you're going to understand this paradox, and you're going to see how something can be both enormous and insignificant at the same time. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The Milky Way stretches 100,000 light-years from one edge to the other. Let me put that in perspective right away, because it's easy to say those words without understanding what they actually mean. Light travels at 671 million miles per hour. That's fast enough to circle the Earth 7.5 times in 1 second. At that speed, light takes 8 minutes to reach us from the Sun, and it takes 100,000 years to cross the Milky Way from edge to edge. 100,000 years of continuous travel at the fastest speed possible in the universe. In the time it takes light to cross our galaxy once, humans went from cave paintings to spacecraft, from stone tools to quantum computers, from small nomadic bands to a global civilization of 8 billion people. That's the scale we're talking about. And that's just the visible disk. The Milky Way has more structure than just the flat spiral you see in pictures. Surrounding the disk is a halo, a roughly spherical region extending perhaps 300,000 light-years from the center. The halo contains old stars, ancient stars that formed when the galaxy was young. And it contains something else: dark matter. We can't see dark matter directly because it doesn't interact with light. It doesn't emit photons, doesn't absorb them, doesn't reflect them. But we know it's there because we can measure its gravitational effects. The stars in the outer parts of the Milky Way orbit faster than they should based on the visible matter alone. The only explanation that fits the observations is that there's additional mass out there, invisible mass, creating extra gravity. Current estimates suggest that about 85% of the matter in the Milky Way is dark matter. Only 15% is the normal matter we can see, the stuff that makes up stars and planets and gas clouds and us. The dark matter halo is massive, perhaps containing 1 trillion times the mass of the Sun. So when we talk about the Milky Way's size, we have options. The visible disk is 100,000 light-years across. The dark matter halo extends 300,000 light-years or more. Both are legitimate measurements. Both lead to staggering numbers. Now, inside this enormous structure, the Milky Way contains somewhere between 100 billion and 400 billion stars. That's a huge range, and it reflects the difficulty of counting stars in a galaxy you're inside of. Many stars are hidden behind dust clouds. Many are too faint to see individually, even with our best telescopes. Many are clustered together so densely that they blend into a single point of light. But whether it's 100 billion or 400 billion, it's an incomprehensible number, and each one of those stars is unique. They come in an astounding variety of sizes, temperatures, colors, and lifespans. Understanding this diversity is crucial to understanding the Milky Way's true nature. Our Sun is just one of these stars. It sits about 26,000 light-years from the galactic center, tucked into a minor spiral arm called the Orion Spur. We're not at the center of anything special. We're in the suburbs, in a relatively quiet neighborhood where stars aren't packed too densely, and violent events like supernovae are rare enough that life had time to develop and survive. This location matters more than you might think. If we were closer to the galactic center, in the dense bulge where stars are packed tightly together, life would face constant threats. Nearby stars, passing close enough to disturb planetary orbits. More frequent supernovae, bathing the region in deadly radiation. Intense gravitational interactions that could eject planets from their systems entirely. The central regions are chaotic, dangerous places. Out here in the suburbs, things are calmer. Stars maintain stable orbits. Supernovae are rare enough that life has time to evolve between catastrophes. The radiation environment is relatively benign. Some astronomers think there might be a galactic habitable zone, a region where conditions are most favorable for life, too close to the center, and it's too dangerous, too far out, and there aren't enough heavy elements to form rocky planets. But in the middle regions, like where we are, conditions might be just right. Our Sun orbits the galactic center once every 230 million years. That's one galactic year, a useful way to think about cosmic timescales. Every star you can see with your naked eye on a clear night is part of the Milky Way. Every constellation, every planet visible in the sky, all of it belongs to this one structure. For most of human history, we didn't even know there was anything beyond it. The Milky Way was our entire universe. Ancient peoples looked up at that band of light and wondered what it was. The Greeks thought it was milk spilled by the goddess Hera, hence the name Milky Way. Norse mythology described it as a path for souls to reach the afterlife. In China, it was seen as a celestial river. Beautiful stories. But they had no idea of the true nature or scale of what they were seeing. The first hint came in the early 1600s, when Galileo pointed his telescope at the Milky Way. What he discovered was revolutionary. That faint band of light wasn't a cloud or a river of milk. It was made of stars, countless stars, so densely packed and so far away that they blended together into a faint glow visible to the naked eye. This was profound. It meant the universe contained far more stars than anyone had imagined. But it still didn't tell us what the Milky Way actually was. Was it the entire universe, containing all the stars that exist? Or was it just one structure among many? That question wouldn't be answered for another 300 years. And here's where things get interesting, because this is where the paradox begins to emerge. The Milky Way is genuinely large. It's not an exaggeration to say it's one of the biggest galaxies in the universe. When astronomers survey the cosmos, counting and categorizing galaxies, they find that the vast majority are dwarf galaxies. Small structures containing anywhere from a few million to a few billion stars. Tiny compared to the Milky Way. The large Magellanic Cloud, one of our satellite galaxies visible from the southern hemisphere, contains about 30 billion stars. That sounds like a lot, but it's less than 1/10 what the Milky Way has. The small Magellanic Cloud has only a few billion stars, and there are dozens of even smaller dwarf galaxies orbiting us, some containing fewer than 1 million stars. These tiny galaxies are held in orbit by the Milky Way's gravity, slowly being pulled apart and absorbed over billions of years. We're literally eating our smaller neighbors, growing through cosmic cannibalism. When you account for all the dwarf galaxies throughout the universe, it turns out that about 95% of all galaxies are smaller than the Milky Way. 95%. That puts our home galaxy in the top 5% by size. We're not living in some average, middle-of-the-road galaxy. We're living in one of the largest structures of its kind in the entire cosmos. Think about that for a moment. Out of all the galaxies that exist, out of the hundreds of billions scattered across the observable universe, the Milky Way is in the top tier. It's exceptional. Most galaxies are dwarfs with just a few billion stars or less. The Milky Way, with its hundreds of billions of stars, is a giant by comparison. The only galaxies significantly larger than the Milky Way are giant elliptical galaxies. These are massive structures containing trillions of stars, often found at the centers of galaxy clusters. They form through mergers, when multiple large galaxies collide and combine over billions of years. The largest known galaxy, IC 10101, contains about 100 trillion stars and stretches about 6 million light-years across, 60 times wider than the Milky Way. Absolutely enormous. But these giant ellipticals are rare. For every giant elliptical, there are hundreds or thousands of spiral galaxies like ours, and millions of dwarf galaxies. By number, the Milky Way is exceptional. It's in the upper tier of galactic size. So, when people say the Milky Way is large, they're not being poetic. They're stating a fact. Measured against the population of galaxies in the universe, we live in one of the big ones. Our galaxy contains more stars than most, stretches farther than most, and has more mass than most. That's genuinely impressive. It means we're not in some insignificant corner of the cosmos. We're in a massive, impressive structure that towers over most other galaxies. But here's where the paradox starts. Because while the Milky Way is large compared to most galaxies, it's also part of much larger structures. And when you start looking at those structures, even a large galaxy like ours starts to seem small. The Milky Way isn't floating alone in empty space. It has neighbors. The closest large galaxy to us is Andromeda, sitting about 2.5 million light-years away. Andromeda is actually bigger than the Milky Way. It contains roughly 1 trillion stars, about twice to 3 times what we have. It stretches about 220,000 light-years across, more than twice our diameter, and it's headed toward us, approaching at about 68 miles per second. In about 4.5 billion years, the two galaxies will collide and merge. But don't worry about that. By the time it happens, the Sun will be nearing the end of its life, and Earth will likely be uninhabitable anyway. The Milky Way and Andromeda, along with about 50 other smaller galaxies, form what astronomers call the local group. This is our cosmic neighborhood. Most of the galaxies in the local group are dwarfs, small structures with just a few billion stars each. The Milky Way and Andromeda are the two dominant members, like two large cities surrounded by small towns. The local group spans about 10 million light-years across. That's 100 times the diameter of the Milky Way. Already, we're seeing the scale shift. The Milky Way seemed enormous at 100,000 light-years, but the local group is 100 times larger. Our entire galaxy, with all its hundreds of billions of stars, is just one component in this larger structure, and the local group is just a tiny piece of something much bigger. It's part of the Virgo supercluster. A supercluster is a cluster of galaxy clusters. Instead of individual galaxies, we're now talking about groups of galaxies, all gravitationally bound together into enormous structures. The Virgo supercluster contains at least 100 galaxy clusters and groups. The largest is the Virgo cluster itself, sitting about 54 million light-years from us and containing somewhere between 1,000 and 2,000 galaxies. Some of these galaxies are massive, far larger than the Milky Way. The Virgo supercluster as a whole contains about 100 trillion stars spread across about 110 million light-years. Let me put that in perspective. The Milky Way seemed large at 100,000 light-years across. The Virgo supercluster is 1,100 times wider. If the Milky Way were a single room in a house, the Virgo supercluster would be an entire city. Our entire galaxy, with all its hundreds of billions of stars, is just a tiny speck in this larger structure. But we're not done. Not even close. In 2014, astronomers discovered something even bigger. They found that the Virgo supercluster itself is just a small part of an even more massive structure called Laniakea. The name comes from Hawaiian and means immeasurable heaven. It's fitting. Laniakea is a supercluster of superclusters. It contains about 100,000 galaxies spread across 520 million light-years. All of these galaxies, including ours, are slowly moving toward a region in the center called the Great Attractor. The Milky Way isn't sitting still in space. We're falling, along with everything else in Laniakea, toward this central region at about 370 miles per second. That's over 1 million miles per hour. And you don't feel a thing, because everything around you is moving together. If you shrunk Laniakea down so that the Milky Way was the size of a grain of sand, Laniakea itself would be about as big as a large room. We've gone from thinking our galaxy is everything to realizing it's less than a speck of dust in a structure so vast it defies easy comprehension. And even Laniakea isn't the end. When we zoom out even further, we see that the universe is filled with these structures. Superclusters, separated by vast voids, empty regions of space where very few galaxies exist. The universe, at the largest scales, looks like a cosmic web, filaments of galaxies stretching across billions of light-years, with enormous empty voids between them. The largest known structure in the universe is the Hercules Corona Borealis Great Wall. It's a galactic filament stretching about 10 billion light-years across. That's roughly 1/10 the diameter of the observable universe. At this scale, even superclusters like Laniakea seem small. The Milky Way is utterly insignificant. It's not even visible at this scale. If you made a map of the Hercules Corona Borealis Great Wall and tried to mark the Milky Way's location, you couldn't. It would be too small to represent. This is the paradox. The Milky Way is genuinely large, one of the biggest galaxies in the universe. And it's also tiny, invisible against the largest cosmic structures. Both things are true simultaneously. Scale is relative. It depends entirely on what you're comparing. Let me give you another way to understand this paradox. Imagine you could travel at the speed of light, 671 million miles per hour, fast enough to circle the Earth 7.5 times in 1 second. At that speed, you could fly to the moon in about 1.3 seconds. You could reach the sun in 8 minutes. You could visit Proxima Centauri, the nearest star, in 4.24 years. Now imagine you decided to cross the entire Milky Way. You start at one edge of the galactic disk and head toward the opposite edge, traveling at light speed, never slowing down, never stopping. It would take you 100,000 years. 100,000 years of continuous travel at the fastest possible speed. You'd see billions of stars pass by. You'd cross vast clouds of gas and dust, regions where new stars are being born. You'd pass through the galactic center, where stars are packed densely and a supermassive black hole lurks. You'd see star clusters, nebulae, planetary systems, all the wonders of our galaxy. And after 100,000 years, you'd finally reach the far edge. That's the scale of the Milky Way. Even at light speed, it's a 100,000-year journey. Now, to reach Andromeda, the nearest large galaxy, you'd need another 2.5 million years. To cross the Virgo supercluster would take over 100 million years. To traverse Laniakea would require more than 500 million years. These numbers are so large they stop having meaning. Your brain can't really grasp 100,000 years or 500 million years in any intuitive way. But you don't need to intuitively grasp these scales to understand them conceptually. You can know intellectually that the Milky Way is 100,000 light-years across, even if you can't feel what that distance means. And that knowledge changes you. It has to. When you understand that your entire existence, everything you've ever known or experienced, has happened in a galaxy that's one of hundreds of billions, it shifts your perspective. Now, let's talk about what fills this enormous space. Because the Milky Way isn't just empty distance. It's populated with hundreds of billions of stars, each one different. They range from tiny red dwarfs, barely massive enough to sustain nuclear fusion, to supergiant stars that would engulf the orbit of Jupiter if you put them where our Sun is. Red dwarfs are the most common type of star in the Milky Way. They make up about 70 to 80% of all stars. They're small, dim, cool stars with masses between about 8% and 40% of the Sun's mass. They burn their hydrogen fuel so slowly that they can last for trillions of years. None of the red dwarfs that have ever formed have died yet. Even the oldest ones, born shortly after the Big Bang over 13 billion years ago, are still burning fuel. They'll outlive every other type of star. When the universe is old and cold, and most stars have died, red dwarfs will still be shining, the last lights in a darkening cosmos. But despite their numbers, red dwarfs contribute very little to the galaxy's total light. They're so dim that even the nearest ones are invisible to the naked eye. Proxima Centauri, the closest star to our Sun, is a red dwarf. It's only 4.24 light-years away, practically next door in cosmic terms. But you can't see it without a telescope because it's so faint. If red dwarfs are the galaxy's worker bees, numerous but dim, then stars like our Sun are the middle class. Yellow dwarf stars make up about 7 to 8% of all stars. They're medium-sized, medium temperature, burning steadily for about 10 billion years. Our Sun is about halfway through its main sequence lifetime. It has another 5 billion years before it exhausts the hydrogen in its core. When that happens, it will swell into a red giant, possibly engulfing the inner planets. Eventually, it will shed its outer layers, creating a planetary nebula. What remains will be a white dwarf, slowly cooling over billions of years. Larger stars, those with masses 2 or 3 times the Sun's, burn hotter and faster. They live for only a few 100 million to 1 billion years. They're more luminous than the Sun, contributing more light despite being less common. And then there are the giants. Stars with masses 10, 20, 50, or even over 100 times the Sun's mass. These are rare, making up less than 1% of all stars, but they dominate the galaxy's light output. A single massive star can be tens of thousands or even millions of times more luminous than the Sun. They burn through their fuel at incredible rates, living fast and dying spectacularly. The most massive stars live for only a few million years. They fuse hydrogen into helium, then helium into carbon and oxygen, then carbon into heavier elements. They work their way up the periodic table, creating heavier and heavier elements in their cores. Silicon, sulfur, calcium, iron. But when they create iron, the process stops producing energy. Fusing iron absorbs energy instead of releasing it. The core can no longer support itself against gravity. It collapses in a fraction of a second. The collapse is so violent that it rebounds in a catastrophic explosion, a supernova. For a brief time, that single dying star outshines the entire galaxy. It blasts its outer layers into space at speeds of tens of thousands of miles per second. The explosion creates a shock wave that races outward, sweeping up and heating the surrounding gas. And in the extreme conditions of the explosion, elements heavier than iron are created. Gold, platinum, uranium, all the heaviest elements in the universe. These elements, scattered by the supernova, enrich the interstellar medium. They become part of the next generation of stars and planets. Every atom of gold in a wedding ring, every atom of uranium in a nuclear reactor was created in a supernova explosion. These events are rare in any given region of the galaxy. On average, the Milky Way experiences about 1 to 3 supernovae per century. But over billions of years, countless supernovae have enriched the galaxy with heavy elements. This is why we exist. Rocky planets need heavy elements. Silicon for the rocks, iron for the core, oxygen for the atmosphere, and water. None of these existed in the early universe. They were all created in stars and scattered by supernovae. Earth is made of stardust in the most literal sense possible. Red dwarfs are the most common type of star in the Milky Way. They make up about 70 to 80% of all stars. They're small, dim, cool stars with masses between about 8% and 40% of the Sun's mass. They burn their hydrogen fuel so slowly that they can last for trillions of years. None of the red dwarfs that have ever formed have died yet. Even the oldest ones, born shortly after the Big Bang over 13 billion years ago, are still burning fuel. They'll outlive every other type of star. When the universe is old and cold, and most stars have died, red dwarfs will still be shining. Then there are stars like our Sun, yellow dwarf stars. These make up about 7 to 8% of all stars. They live for about 10 billion years, spending most of that time steadily fusing hydrogen into helium in their cores. Our Sun is about halfway through its main sequence lifetime. It has another 5 billion years or so before it runs out of core hydrogen and begins to evolve into a red giant. Larger stars, those with masses 2 or 3 times the Sun's mass, burn hotter and faster. They live for only a few 100 million to a billion years. And the real giants, stars with masses 10, 20, 50 times the Sun's mass, live fast and die young. They burn through their fuel in just a few million years. They're so massive that they can fuse heavier and heavier elements in their cores until finally they create iron, and then they die catastrophically. When a massive star tries to fuse iron, the process absorbs energy instead of releasing it. The core collapses in a fraction of a second. rebounding in a violent explosion called a supernova. For a brief time, that single star can outshine an entire galaxy. It blasts its outer layers into space, scattering all the elements it created. Every atom in your body, heavier than hydrogen and helium, was forged in a star. The calcium in your bones came from a supernova. The iron in your blood was created in the core of a massive dying star. The oxygen you breathe was synthesized in a star that lived and died before our sun formed. You are, quite literally, made of the Milky Way. Your atoms have been recycled through multiple generations of stars. They've traveled across the galaxy, scattered by stellar explosions, eventually finding their way into the cloud of gas that collapsed to form our solar system 4.6 billion years ago. In that sense, you're not separate from the Milky Way. You're part of it. The galaxy isn't just your home, it's your origin, your substance, your context. The stars aren't evenly distributed throughout the galaxy. In the central bulge, stars are packed much more densely, sometimes only a few light months apart. If you lived on a planet in the galactic bulge, your night sky would be spectacular. Thousands of stars, bright enough to cast shadows. No true darkness, even at night, but it would also be more dangerous. Supernovae would be more frequent. Gravitational interactions between stars would be more common. The central bulge isn't a friendly place for life. At the very center sits Sagittarius A star, a supermassive black hole containing about 4 million times the mass of the Sun. Every star in the galaxy, including our Sun, orbits around this central region. We complete one full orbit every 230 million years. That's called a galactic year. The last time our Sun was in this position in its orbit, dinosaurs didn't exist yet. The supercontinent Pangaea was just beginning to form. Since then, we've made one complete lap around the galaxy. Dinosaurs rose and fell. Mammals evolved and diversified. Humans appeared and built civilizations, all in one galactic year. This puts Earth's history in a humbling perspective. Everything that's ever happened on our planet, all the life that's emerged and evolved and gone extinct, has occurred during less than 20 galactic years. The Earth itself has only existed for about 20 galactic years. The galaxy is so much older than our world. It was already ancient when our solar system formed. The supermassive black hole at the galactic center is one of the most extreme objects in the Milky Way. 4 million solar masses compressed into a region smaller than Mercury's orbit. The gravity there is so intense that space and time are severely warped. Stars, orbiting close, move at speeds up to a few percent the speed of light. We've tracked these stars for decades with incredible precision. One star, S2, orbits the black hole in about 16 years. At closest approach, it moves at about 3,100 miles per second, about 2% the speed of light. By tracking such stars, astronomers have measured the black hole's mass precisely and tested Einstein's general relativity in extreme conditions. And relativity holds up. In the spiral arms, you find clusters of young hot stars. These are regions of active star formation, where giant clouds of gas collapse under their own gravity to create new stars. The spiral arms aren't permanent structures. They're density waves, regions where stars and gas are temporarily compressed as they orbit. Individual stars drift in and out of the arms over millions of years. Our Sun moves in and out of the Orion Spur on a timescale of tens of millions of years. This differential rotation, where different parts of the galaxy orbit at different speeds, is what creates and maintains the spiral structure. Stars closer to the center complete their orbits faster. Stars farther out take longer. This creates a shearing effect, stretching and winding up the galaxy's structure. But spiral arms aren't just the result of this shearing. They're density waves, patterns that propagate through the disk like ripples on a pond. As the galaxy rotates, these density waves move through it at a different speed than the stars themselves. When stars and gas clouds enter a density wave, they slow down slightly, piling up. The increased density triggers star formation in the gas clouds. New, massive stars light up, making the spiral arm visible. But those stars don't stay in the arm forever. They continue their orbits, eventually leaving the density wave behind. The spiral pattern persists, but it's made up of different stars at different times. It's similar to a traffic jam on a highway. The jam itself doesn't move much, but different cars are constantly entering and leaving it. The spiral arms are the jam. The stars are the cars. This is why spiral arms are bright. They're regions of active star formation, full of young, hot stars that haven't had time to drift away yet. Our sun's orbit around the galaxy isn't a perfect circle. It's slightly elliptical, and it also oscillates up and down relative to the galactic plane. We cross through the plane about every 30 to 40 million years, moving above it, then back through, then below it, then back through again. This vertical oscillation might have consequences for Earth. Some researchers have proposed that passages through the denser midplane could increase the rate of comet impacts. As we pass through, gravitational interactions with dense molecular clouds might disturb the Oort cloud, sending comets toward the inner solar system. It's speculative, but there's some evidence that major extinction events on Earth might correlate with these passages through the galactic plane. Whether this connection is real or coincidental is still debated. But it's a reminder that the galaxy's structure and our motion through it might affect life on Earth in subtle ways. The entire Milky Way is also moving through space. It's not stationary relative to other galaxies. We're falling toward Andromeda at about 68 miles per second. We're also moving as part of the local group's motion through space. And the local group itself is moving, pulled by the gravity of larger structures like the Virgo supercluster and Laniakea. Our total velocity through space relative to the cosmic microwave background is about 370 miles per second, over 1 million miles per hour. You don't feel it because everything around you is moving with you. But relative to the ancient light from the Big Bang, we're racing through the cosmos at incredible speed. This motion is shaped by the distribution of matter around us. We're not moving randomly. We're following the flow of cosmic structure, pulled by gravity toward regions of higher density. The Great Attractor, a concentration of mass in the direction of the Centaurus and Hydra constellations, is pulling our entire region of space toward it. Beyond that, there are even larger structures influencing our motion. The Shapley supercluster, an enormous concentration of galaxies about 650 million light-years away, exerts a gravitational pull that affects a significant portion of the observable universe. We're being pulled toward it, along with countless other galaxies. This is what cosmic structure means. Everything is connected through gravity. Every galaxy influences every other galaxy, at least slightly. The Milky Way's motion through space is determined by the distribution of matter across hundreds of millions of light-years. We're part of a vast gravitational dance that's been choreographed by the structure of the universe itself. Between the stars, filling the space, is gas and dust. the interstellar medium. It's not empty space. It's filled with thin clouds of hydrogen gas, denser molecular clouds where stars form, and dust grains that scatter and absorb starlight. About 10 to 15% of the Milky Way's visible mass is in gas and dust, the raw material for future generations of stars. These dust clouds are why we can't see across the entire galaxy. They block our view, creating the dark lanes you see in the Milky Way's band of light. To see through the dust, astronomers use infrared and radio telescopes. Different wavelengths reveal different aspects of the galaxy's structure. Now, scattered among those hundreds of billions of stars, there might be life. Current estimates suggest that tens of billions of planets in the Milky Way might be potentially habitable. Places where liquid water could exist, where temperatures are moderate, where life might emerge. We don't know how many actually have life. We know it happened at least once, here on Earth, but we don't know how common it is. Maybe life emerges inevitably wherever conditions are right. Or maybe it's so improbable that Earth is the only place it ever happened. The question of life's prevalence is one of the most profound we face. Because if life is common, if it emerges on even a small fraction of habitable planets, then the Milky Way could be teeming with it. Tens of billions of habitable planets, times even a small percentage, equals billions of worlds with life. Imagine that for a moment. Billions of worlds throughout the Milky Way where life has emerged. Some might still be in the microbial stage, simple single-celled organisms in the oceans. Others might have complex ecosystems, forests and reefs teeming with diverse species. A few might have intelligent life, civilizations capable of technology, space travel, perhaps even contemplating their own place in the galaxy. If this is true, the Milky Way is not just a collection of stars and gas and dust. It's an ecosystem on a galactic scale, a place where life emerges, evolves, adapts, thrives, and perhaps spreads. But we have no evidence of this yet. We've found thousands of exoplanets, planets orbiting other stars. The first confirmed exoplanet orbiting a sun-like star was discovered in 1995. Since then, missions like Kepler and TESS have found thousands more. We now know that planets are common. Almost every star has at least one planet. Many have multiple planets. And a significant fraction of those planets are in the habitable zone, the region where temperatures allow liquid water to exist on the surface. Liquid water is crucial because all life on Earth depends on it. Water is an excellent solvent, allowing complex chemistry to occur. It remains liquid over a wide temperature range. It's abundant in the universe. If life exists elsewhere, it probably needs water. So, astronomers focus on finding planets in the habitable zone, the region around a star where temperatures are right for liquid water. For a star like our Sun, the habitable zone extends from about 0.9 to 1.5 astronomical units. Earth sits right in the middle of this zone, at 1 astronomical unit. Mars is near the outer edge. Venus is too close, too hot. But habitable zones vary depending on the star. Red dwarfs are cooler, so their habitable zones are closer in. Larger, hotter stars have habitable zones farther out. And the habitable zone is just one factor. A planet also needs the right size to hold an atmosphere. Too small, like Mercury, and gravity isn't strong enough to retain gases. Too large, and it becomes a gas giant, like Jupiter. It needs geological activity to recycle carbon and regulate climate over billions of years. it needs a magnetic field to protect against stellar radiation. It probably needs a large moon to stabilize its axial tilt, preventing extreme climate swings. Earth has all of these factors. It's the right size, in the right place, orbiting the right kind of star. It has plate tectonics, recycling carbon through volcanic activity. It has a strong magnetic field generated by a molten iron core. It has a large moon that stabilizes its rotation. All of these factors combined to create a world where life could emerge and persist for billions of years. How many other worlds have this combination of factors? We don't know. Statistical studies suggest that Earth-sized planets in habitable zones might be fairly common. Perhaps 20 to 50% of Sun-like stars have them. Apply that to the Milky Way's population of hundreds of billions of stars, and you get tens of billions of potentially habitable worlds. But potentially habitable doesn't mean inhabited. Life has to actually emerge. And we don't know how likely that is. On Earth, life appeared relatively quickly after the planet formed and cooled. The earliest evidence of life dates to about 3.8 billion years ago, only about 700 million years after Earth formed. That suggests life might emerge readily wherever conditions are right. Or it might mean we got incredibly lucky. With a sample size of 1 Earth, we can't tell the difference between common and rare. If we found even one other example of life, anywhere, on Mars, on Europa, on a planet orbiting another star, it would suggest life is common. But so far, we've found nothing. No unambiguous signs of life, anywhere except Earth. The search continues. Missions to Mars look for signs of ancient microbial life in rocks. Missions to Europa and Enceladus will search for life in subsurface oceans. The James Webb Space Telescope examines the atmospheres of exoplanets, looking for biosignatures, gases like oxygen and methane that might indicate biological processes. SETI, the search for extraterrestrial intelligence, listens for signals from other civilizations. So far, nothing conclusive. But the search has barely begun. We've examined a tiny fraction of the galaxy. We've studied a handful of nearby exoplanets. We've listened for signals from a small number of stars. The Milky Way is vast. If life exists, we might simply not have looked in the right places yet. Or we might be alone. Maybe life is incredibly rare, so improbable that it happened only once in the entire galaxy. Maybe Earth is special, not just in degree, but in kind. The only world where chemistry became biology, where molecules became life. That would be profound in a different way. It would mean we're alone, unique, the only consciousness in our galaxy. It would make Earth precious beyond measure, the only place where the universe has become aware of itself. We don't know which scenario is true. Maybe the galaxy is full of life, and we'll find it. Maybe we're alone, and we'll never find anyone else. Both possibilities are humbling. Both change how we think about our place in the cosmos. And if life is common, intelligent life might still be rare. Life existed on Earth for 3.5 billion years before intelligence emerged. Maybe most planets with life remain microbial forever. Maybe intelligence is incredibly rare. This is the Fermi paradox. In a galaxy as large and as old as the Milky Way, with so many stars and so many potential habitable worlds, where are all the aliens? Various answers have been proposed. Maybe we're among the first. Maybe civilizations destroy themselves. Maybe space travel is harder than we think. Maybe they're out there, but the distances are simply too vast for contact. Each of these explanations has implications. If we're among the first intelligent species in the galaxy, it means we have enormous responsibility. How we develop, how we treat our world, how we eventually spread into space, might set a template for others who come after. We might be pioneers, exploring and settling a galaxy that's mostly empty. That's exciting, but also sobering. It means there's no one out there to save us if we make mistakes. No advanced civilizations to guide us or help us through challenges. We're on our own, figuring things out as we go. If civilizations tend to destroy themselves, that's even more sobering. It would suggest there's a great filter, some challenge that most civilizations fail to overcome. Maybe it's nuclear war, or climate change, or some technology we haven't invented yet that proves too dangerous. Maybe intelligence is self-limiting, burning bright and brief before collapsing. If that's true, our survival is not guaranteed. We might face challenges that previous civilizations failed to overcome, and unless we're careful, we might fail too. If space travel is harder than we think, it would explain why we haven't seen evidence of galactic colonization. Maybe the distances are simply too vast, the energy requirements too high, the time scales too long. Maybe civilizations arise, flourish on their home worlds, but never spread beyond their local solar systems. That would make the galaxy a collection of isolated islands, each one populated but separated from the others by unbridgeable gulfs we'd never meet. We'd spend our existence wondering if others are out there, never able to confirm it. Or maybe they're out there, and the distances really are the problem. In a galaxy 100,000 light-years across, even light takes an incomprehensible amount of time to travel between distant points. Radio signals, traveling at light speed, would take decades or centuries or millennia to cross the gulf between civilizations. A conversation is impossible when each exchange takes thousands of years. By the time you receive a reply, your civilization might have changed beyond recognition. The people who sent the original message would be long dead, their culture possibly extinct. At those scales, communication becomes almost meaningless. You're not having a conversation. You're sending messages into the deep future, hoping someone might find them. And perhaps receiving messages from the deep past, sent by civilizations that might no longer exist. This is what the scale of the Milky Way does to the possibility of contact. It makes it difficult, perhaps impossible, regardless of how common intelligent life might be. The galaxy is simply too large, the distance is too vast, the time scales too long. We might be surrounded by other civilizations, scattered among the hundreds of billions of stars, and we'd still be effectively alone, isolated by the sheer scale of space. Some scientists have proposed that advanced civilizations might use different communication methods we haven't discovered yet. Maybe they've moved beyond radio, using technologies we can't imagine. Maybe they communicate using methods that are invisible to us. Or maybe they're deliberately staying quiet. The dark forest hypothesis suggests that broadcasting your presence might be dangerous. If there are predatory civilizations out there, ones that view emerging civilizations as threats, staying quiet might be the smart strategy. Hide, listen, but don't transmit. Don't reveal your location. It's a grim scenario, but possible. We don't know how other intelligences might behave. They might be friendly, or hostile, or indifferent. Broadcasting into space, as we've been doing for the last century, might be wise or incredibly foolish. We won't know until we either make contact or don't. For now, we continue searching. We listen for signals. We look for signs of life on other worlds. We map the galaxy, counting stars and planets, trying to understand how common habitable worlds might be. And we wonder, in a galaxy as large as the Milky Way, are we alone? Or are there others out there, asking the same question, looking up at their own skies, wondering if anyone is listening? In a galaxy 100,000 light-years across, even if there are thousands of civilizations, they might be separated by distances of thousands of light-years each. Light takes thousands of years to travel between them. A message would take millennia to arrive, and by the time you received a reply, your civilization might have changed beyond recognition. Communication at galactic scales involves time lags that exceed the lifespan of civilizations. Maybe that's why the galaxy is silent. The scale isolates us. But before we go further into the search for life, let's understand what actually fills the space between those hundreds of billions of stars. Because the Milky Way isn't just stars floating in a void. The interstellar medium, the space between stars, is filled with gas and dust. About 10 to 15% of the visible matter in the Milky Way exists in this form. The raw material for future generations of stars. And this material has structure, complexity, beauty. Some regions are dense, giant molecular clouds containing hundreds of thousands of times the mass of the Sun. These are stellar nurseries, the places where new stars are born. Other regions are sparse, blown clear by stellar winds and supernova explosions. They contain only a few atoms per cubic centimeter. That's more empty than the best vacuum we can create in laboratories on Earth. The densest regions, the molecular clouds, are where stars form. When a cloud gets dense enough and cold enough, gravity begins to pull clumps of it together. These clumps contract, getting denser and hotter. If a clump gathers enough mass, the core temperature rises to about 10 million degrees. At that temperature, hydrogen nuclei start to fuse into helium, releasing enormous amounts of energy. A star is born. This process is happening right now in clouds throughout the Milky Way. The Orion Nebula, visible to the naked eye as a fuzzy patch in Orion's sword, is one of the nearest stellar nurseries. It's about 1,300 light-years away. Inside that nebula, hundreds of new stars have formed in the last few million years. Many are still surrounded by disks of gas and dust, the raw material from which planets will eventually form. The Carina Nebula, about 7,500 light-years away, is one of the largest star-forming regions in the Milky Way. It contains numerous massive stars, some over 100 times the mass of the Sun. These giants burn so hot and bright that they're blasting their surroundings with intense radiation. They'll live fast and die young, exploding as supernovae in just a few million years. Star formation isn't constant throughout the galaxy. It happens in bursts, triggered by events that compress the interstellar medium. When spiral density waves sweep through the disk, they compress gas clouds, triggering star formation. That's why spiral arms are bright. They're where star formation is most active, where young massive stars light up the gas around them. The Milky Way's current star formation rate is relatively modest. We're forming about 1 to 3 solar masses of new stars per year. That might not sound like much, but over 1 billion years, that's 1 to 3 billion solar masses of new stars. Over the galaxy's 13 billion-year history, that adds up. Not all of that mass remains in stars. Massive stars return much of their mass to the interstellar medium when they die. They blow off their outer layers as stellar winds. They explode as supernovae, scattering their contents across light years. This returned material is enriched with heavy elements: carbon, oxygen, silicon, iron, all the elements forged in the star's core. This is how the galaxy enriches itself over time. The first stars, born shortly after the Big Bang, contained only hydrogen and helium, the primordial elements. When they died, they added heavy elements to the mix. The second generation of stars formed from slightly enriched gas. When they died, they added even more heavy elements. Each generation builds on the chemical legacy of previous generations. By now, after 13 billion years of stellar evolution, the interstellar medium in the Milky Way is about 2% heavy elements by mass. That might not sound like much, but it's crucial. It's enough to make rocky planets, enough to make the molecules necessary for life. Without those heavy elements, there would be no Earth, no water, no complex chemistry, no life. The galaxy had to mature, had to go through multiple generations of stars before conditions were right for life to emerge. We're made of recycled stardust, atoms that have been through multiple stellar generations. Your body contains atoms that were once part of other stars, scattered by supernovae billions of years ago. Those atoms drifted through space, were incorporated into new stars and planets, and eventually found their way into you. You're not separate from the Milky Way. You're part of its ongoing story of creation and recycling. These dust clouds between the stars are why we can't see across the entire galaxy in visible light. They block our view, absorbing and scattering starlight. The Great Rift, that dark lane that appears to split the Milky Way's glow, isn't an absence of stars. It's a series of dust clouds lying between us and the galactic center. Without those clouds, the galactic center would dominate our night sky. It would be bright enough to read by, a vast glowing bulge stretching across a significant portion of the sky. But dust dims that light by factors of thousands or more. What we see is a faint band, a hint of the galaxy's true glory. To see through the dust, astronomers use different wavelengths. Infrared light has longer wavelengths than visible light, and it can pass through dust more easily. In infrared, the galaxy lights up. We can see the central bulge, the spiral arms, stars hidden from visible observation. Radio telescopes are even better at penetrating dust. Radio waves have wavelengths measured in inches or feet, far longer than dust particles. They pass through almost unimpeded. Radio observations have mapped the spiral structure of the Milky Way, traced the distribution of hydrogen gas, revealed regions of star formation buried deep within dust clouds. Different wavelengths show different aspects of the galaxy. Visible light shows us hot stars, regions where radiation is most intense. Infrared shows cooler stars and dust clouds heated by embedded stars. Radio shows gas clouds, both neutral hydrogen and the molecular clouds where stars form. X-rays reveal the hottest phenomena. Supernova remnants, gas heated to millions of degrees, material falling into black holes. By combining observations at all these wavelengths, astronomers build a complete picture. It's like seeing the galaxy in different colors, each one revealing hidden details. Now, let's talk about the exotic objects scattered throughout the Milky Way, because it's not just normal stars out there. There are black holes, stellar mass black holes formed from collapsed stars. Current estimates suggest there might be 10 million to 100 million of them in the Milky Way. Most are invisible, silent, detectable only if they have a companion star feeding gas into them. When gas falls into a black hole, it heats up to millions of degrees and emits X-rays. That's how we find them. But solitary black holes, wandering through space with no companion, are essentially invisible. There could be one passing through the solar system right now, and we'd never know unless it passed close enough to a star to cause detectable gravitational effect. Then there are neutron stars, incredibly dense remnants of supernova explosions. A neutron star contains about 1.4 times the mass of the Sun, all compressed into a sphere, about 12 miles across. About 12 miles. A tablespoon of neutron star material would weigh about 1 billion tons on Earth. The density is comparable to an atomic nucleus, but scaled up to the size of a city. Neutron stars have intense magnetic fields, trillions of times stronger than Earth's. Some neutron stars rotate rapidly, spinning dozens or hundreds of times per second. These are pulsars, beaming radiation from their magnetic poles like cosmic lighthouses. Some pulsars are so regular they rival atomic clocks in accuracy. White dwarfs are the cooling cores of stars like our Sun. When a sun-like star exhausts its fuel, it sheds its outer layers, creating a beautiful planetary nebula. What's left behind is the hot core, compressed to about the size of Earth, but containing about 60% of the Sun's original mass. With no nuclear fusion to support it, a white dwarf just cools slowly over billions of years, gradually fading from white-hot to red to eventually black. The oldest white dwarfs in the Milky Way have been cooling for over 10 billion years. They're dim and hard to detect, but they're out there. Ancient relics from the galaxy's early history. Eventually, billions of years from now, they'll cool to the point where they emit no visible light at all. Black dwarfs. Theoretical objects that would be the final endpoint of stellar evolution. None exist yet. The universe isn't old enough for any white dwarf to have cooled completely. But in the far future, when the Milky Way is old and most of its stars have died, black dwarfs will be common. Let's talk about how we actually measured the Milky Way. For most of human history, we didn't even know it was a galaxy. Ancient peoples saw that band of light and told stories, but they had no idea what they were seeing. In the early 1600s, Galileo pointed his telescope at the Milky Way and discovered it was made of stars. Countless stars, so densely packed and far away that they blended together. But it still didn't tell us what the Milky Way was, or how large it might be. The breakthrough came with Edwin Hubble in the 1920s. Hubble was using the most powerful telescope of his time, studying what were called spiral nebulae in the Andromeda Nebula. He found individual stars, including Cepheid variables. Cepheids are special stars that pulsate with a regular period, and their period is directly related to their intrinsic brightness. If you measure how bright they appear from Earth, you can calculate how far away they must be. When Hubble did this for Andromeda, he got a shocking result. It was about 900,000 light-years away, far beyond the Milky Way. Andromeda wasn't a nebula within our galaxy. It was an entire galaxy on its own. This changed everything. The Milky Way wasn't the entire universe. It was just one galaxy among many. And if we could measure the distance to Andromeda, we could start to estimate the size of our own galaxy by comparison. Hubble's discovery launched a revolution in astronomy. Within a few years, it became clear that the universe was filled with galaxies. What astronomers had thought were small nebulae within the Milky Way were actually enormous structures, each containing billions or hundreds of billions of stars. The universe was vastly larger than anyone had imagined. And the Milky Way, far from being everything, was just one of countless galaxies scattered through space. This fundamentally changed how we understand our place in the cosmos. Over the following decades, astronomers worked to map the Milky Way's structure from the inside. It wasn't easy. Imagine trying to draw a map of a city while standing in the middle of it, unable to climb to a high vantage point. You can see nearby buildings clearly, but distant ones are obscured. You can measure the distance to things you can see, but you can't see the overall layout. That's the challenge astronomers faced with the Milky Way. They developed clever techniques to overcome these limitations. They measured distances to globular clusters, dense spherical collections of hundreds of thousands of old stars that orbit in the galactic halo. By mapping where these clusters are, they could estimate the size of the halo and locate the galaxy's center. They studied the motion of stars, measuring their velocities using the Doppler shift. Stars moving toward us show light shifted toward the blue end of the spectrum. Stars moving away show light shifted toward the red. By mapping these motions, astronomers could understand how the galaxy rotates. They found that the Sun orbits the galactic center at about 140 miles per second. That's about 500,000 miles per hour. At that speed, it takes about 230 million years to complete one orbit. They mapped the distribution of neutral hydrogen gas using radio telescopes. Hydrogen emits radiation at a wavelength of 8.3 inches, and this radiation can pass through dust clouds that block visible light. By observing this 21-centimeter radiation, astronomers could trace the spiral arms and map the galaxy's structure, even in regions hidden by dust. They studied the distribution of different types of stars. Young hot stars are found in spiral arms. Old, cool stars are more evenly distributed throughout the disk. Ancient stars populate the halo. By mapping where different populations of stars are, astronomers could understand the galaxy's history and structure. Slowly, painstakingly, over decades of work, a picture emerged. The Milky Way is a barred spiral galaxy. It has a central bar-shaped structure made of stars and gas, extending about 27,000 light-years from end to end. From the ends of this bar, spiral arms wind outward. The disk is about 100,000 light-years in diameter and about 1,000 light-years thick. The central bulge, a roughly spherical concentration of old stars surrounding the center, extends about 10,000 light-years from the core. The halo, containing old stars and globular clusters, extends perhaps 300,000 light-years, and surrounding everything, the dark matter halo, invisible but detectable through its gravitational effects. This structure didn't form all at once. The Milky Way has a history, a story of formation and evolution over billions of years. It began as a cloud of gas in the early universe, about 13 billion years ago. Gravity pulled the gas together, and the cloud began to collapse. As it collapsed, it fragmented into smaller clumps. These clumps formed the first generation of stars. These early stars were different from stars today. They contained only hydrogen and helium, the primordial elements from the Big Bang. No heavy elements existed yet. When these first stars died, many exploding as supernovae, they scattered the first heavy elements into the surrounding gas. The second generation of stars formed from gas, slightly enriched with these heavy elements. Over time, more and more generations of stars lived and died, each one adding to the chemical enrichment. The galaxy developed structure. It formed a rotating disk as angular momentum caused the collapsing gas cloud to flatten. Spiral arms developed as density waves propagated through the rotating disk. The central bulge formed from gas that fell toward the center early in the galaxy's history, and the Milky Way grew by consuming smaller galaxies. We can see evidence of this cannibalism in stellar streams, long ribbons of stars in the halo that are the torn-apart remnants of dwarf galaxies. The Sagittarius dwarf galaxy is currently being absorbed, its stars scattered into a stream that wraps around the Milky Way. Over hundreds of millions of years, those stars will be fully incorporated. They'll become indistinguishable from the Milky Way's native stars. This process of growth through mergers is common. Most large galaxies, including the Milky Way, have grown by consuming smaller ones. It's a violent process, but it's how galaxies build mass over cosmic time, and it continues today. The Milky Way is still eating smaller galaxies, still growing, still evolving. Over the following decades, astronomers refined their measurements. They mapped the distribution of stars, measured distances to globular clusters, studied galactic rotation. They observed the galaxy in different wavelengths, infrared, radio, X-rays, each revealing different aspects of its structure. Slowly, a picture emerged. The Milky Way is a spiral galaxy about 100,000 light-years across, containing hundreds of billions of stars, with a dark matter halo extending much farther. All of this was figured out, despite being stuck inside the galaxy. It required brilliant deduction, careful observation, and mathematical modeling. The history of measuring the Milky Way is a story of expanding horizons. Each generation thought they understood the scale of the cosmos, only to have the next generation discover it was even larger. And this process continues today. We're still learning. We know far more than we did a century ago, but there's still much we don't understand. The Milky Way has existed for about 13 billion years. 13 billion years is an almost incomprehensible span of time. To put it in perspective, if you compressed the entire history of the Milky Way into a single year, our Sun wouldn't form until late August. Earth wouldn't exist until early September. The dinosaurs would appear around Christmas. And all of human history, from the first cities to now, would happen in the last few seconds before midnight on December 31st. We're newcomers to a galaxy that's been around for most of cosmic history. It formed from clouds of gas in the early universe, slowly pulling together under gravity. The first generation of stars contained only hydrogen and helium. When they died, they enriched the gas with heavy elements. Each generation built on the chemical legacy of earlier generations. Our Sun formed about 4.6 billion years ago, a third or fourth generation star. By then, the gas was enriched enough with heavy elements for rocky planets to form. That's why we exist. We needed multiple generations of stars to live and die before conditions were right for a planet like Earth. The Milky Way will continue to exist for billions of years more. In about 4.5 billion years, it will collide and merge with Andromeda, creating a new elliptical galaxy. By that time, the Sun will be dying. Earth might no longer exist in habitable form. But the galaxy will continue. The merger with Andromeda will transform both galaxies over billions of years. Tidal forces will pull out long streamers of stars. Gas clouds will collide, triggering intense bursts of star formation. The spiral structures will be disrupted. Eventually, the two will merge into a single elliptical galaxy nicknamed Milky Way. It will contain about 1 trillion stars. By then, the Sun will likely be gone, having swelled into a red giant and died. This is the fate of the Milky Way, to merge and transform, part of the ongoing evolution of cosmic structure. Eventually, far in the future, star formation will decline as the gas supply is exhausted. The galaxy will fade, becoming a collection of old dying stars and stellar remnants. But that's trillions of years away. For now, the Milky Way is vibrant, actively forming stars, possibly hosting countless forms of life. So, let's return to the original question. How large is the Milky Way? The answer is that scale is relative. Compared to a human, the Milky Way is unimaginably vast. You could live billions of lifetimes and never visit even a tiny fraction of its stars. Compared to most galaxies, the Milky Way is large. It's in the top 5% by size, containing more stars and spanning more space than 95% of all galaxies. Compared to the structures it's part of, the Local Group, the Virgo supercluster, Laniakea, the Milky Way is small, one component among many, a single thread in a vast tapestry. Compared to the observable universe, the Milky Way is almost nothing. The observable universe stretches about 93 billion light-years across. The Milky Way's 100,000 light-years is less than 1,000th of that. All of these perspectives are true. All of them are valid. The Milky Way is simultaneously large and small, significant and insignificant, exceptional and ordinary. This is the paradox of scale, and it reveals something profound about reality. Scale is not absolute. It's contextual. What matters is what you're comparing. When you can hold multiple scales in your mind at once, when you can appreciate that something can be both enormous and tiny depending on your perspective, you start to understand how the universe really works. This has implications beyond astronomy. From a human perspective, what happens on Earth matters enormously. Our lives, our relationships, our struggles, these things are significant to us. From a cosmic perspective, Earth is invisible. Our entire planet is a pale blue dot lost in the vastness of space. Both perspectives are true. Earth matters to us, and Earth is insignificant cosmically. Understanding this paradox, holding these contradictory truths simultaneously, is what it means to truly grasp cosmic scale. It's humbling and empowering at the same time. Humbling because it shows us how small we are. Empowering because we figured this out. Despite being tiny, we measured the Milky Way. We discovered superclusters. We mapped the cosmic web. We understood our place in structures, billions of light-years across. That's extraordinary. There's one more aspect of scale we need to consider: time. The Milky Way is 13 billion years old. If you compress that history into a single year, human civilization would occupy the last 4 seconds before midnight on December 31st. Everything we think of as human achievement would happen in those final 4 seconds. Agriculture, writing, cities, empires, science, all of it. The dinosaurs ruled Earth for 165 million years. In the galactic year, that's about 4.5 days. They existed far longer than we have. Humans, Homo sapiens, have existed for about 300,000 years. In the galactic year, that's about 20 minutes. Our technological civilization, capable of studying the cosmos, has existed for less than 100 years. In the galactic year, that's about 2 seconds. We've only been capable of measuring the Milky Way for the cosmic equivalent of 2 seconds. And in those 2 seconds, we've achieved something remarkable. We've understood the scale of our home. We've measured structures billions of times larger than ourselves. We've grasped time spans billions of times longer than our lifespans. From a temporal perspective, we're incredibly young. The galaxy existed for 13 billion years before we appeared. It will continue for billions of years after we're gone. Our species is a brief flicker in cosmic time. And yet, in that brief flicker, we've understood the scale. This is the full picture. Spatial scale, 100,000 light-years across. Temporal scale, 13 billion years old. And within that vast structure, operating on those immense scales, tiny and brief, us. The paradox is complete. We're insignificant and significant. Tiny and capable of grasping the enormous. Brief and able to comprehend the ancient. The Milky Way's scale makes us small. Our understanding of that scale makes us remarkable. Both things are true. Both matter. And perhaps that's the deepest truth about understanding the Milky Way's scale. It's not just an exercise in astronomy. It's a philosophical journey. It changes how you see yourself, your life, your place in the grand scheme of things. When you truly understand that you're living on a small planet, orbiting an ordinary star in the suburbs of a large galaxy, one of hundreds of billions of galaxies in the observable universe, it shifts something fundamental. The problems that seem overwhelming in your daily life, the stresses and worries and conflicts, they don't disappear. But they get contextualized. They become part of a much larger picture. You're part of a vast cosmic story that's been unfolding for 13.8 billion years. You exist for a brief moment in that story. A few decades, if you're lucky. And then you'll be gone. Your atoms recycled back into the universe. From a cosmic perspective, your individual life is insignificant. Brief, small, quickly forgotten. But, from a human perspective, your life is everything. It's the only one you get. It's where you experience love, joy, wonder, pain, growth, meaning. Both perspectives are valid. You are cosmically insignificant and personally meaningful. The Milky Way is enormous and tiny. The universe is vast and you are small. All of these contradictions are true simultaneously. And understanding this, really grasping it, is what it means to have a cosmic perspective. It's humbling because it shows you your true scale. You're a temporary arrangement of atoms on a small world in a large galaxy in an even larger universe. But it's also empowering, because despite being so small and brief, you can understand the cosmos. You can measure galaxies billions of light years away. You can comprehend time spans billions of years long. You can grasp your place in the grand scheme of things. No other species we know of can do that. You are the universe's way of knowing itself. A collection of atoms arranged in such a way that they can contemplate atoms, stars, galaxies, the cosmos itself. That's remarkable. That makes you special, even in your insignificance. So, when you feel small, when the vastness of the Milky Way and the universe beyond it makes you feel insignificant, remember this: you are small. That's true. But you're also capable of grasping the large. You're brief, but you can comprehend the ancient. You're one person among billions, but you're also unique. The only arrangement of atoms exactly like you that has ever existed or ever will exist. The Milky Way doesn't care about you. It's indifferent, operating according to physical laws that have nothing to do with human concerns. But you can care about the Milky Way. You can look up at it, understand it, appreciate it. You can recognize that you're made of its atoms, shaped by its history, part of its ongoing story. And that connection, that understanding, that's what makes exploring cosmic scale meaningful. It's not just about the numbers, the light years, and the billions of stars. It's about understanding your place, about seeing yourself as part of something vastly larger, about recognizing both how small you are and how remarkable it is that you exist at all. That's the gift of cosmic perspective. It doesn't make your problems disappear. It doesn't solve the challenges you face in your daily life, but it gives you a framework for thinking about them, a way of seeing yourself and your concerns in the context of deep time and vast space. And sometimes, that perspective is exactly what you need. You're made of atoms forged in stars that died billions of years ago. Those atoms, scattered through the galaxy, recycled into new stars and planets, eventually finding their way into you. You're literally made of the Milky Way. Your body contains calcium from ancient supernovae, iron from stellar cores, oxygen from massive dying stars. In a very real sense, you are the Milky Way's way of knowing itself. You're a collection of atoms that the galaxy has assembled into a form capable of consciousness. The Milky Way created you, and now you're studying it, understanding its scale. That's beautiful. That's profound. And perhaps that's the most important lesson about scale. It's not just about the numbers. It's about perspective, about understanding where you fit in the cosmic order, about recognizing that you're part of something vastly larger than yourself, while also recognizing that your brief existence has meaning and value. The Milky Way doesn't care about you. It's indifferent, operating according to physical laws, but you can care about the Milky Way. You can look up at that band of light and know what you're seeing. You can understand your place in it. You can appreciate both how small you are and how amazing it is that you exist at all. That's what understanding the true scale of the Milky Way gives you. Not just knowledge, but perspective. Not just facts, but wisdom. The ability to hold contradictory truths and recognize that both are valid. You are tiny. You are remarkable. The Milky Way is your home, and it's enormous. The universe is your context, and it's larger still. So when you look up at the night sky and see the Milky Way stretching overhead, that faint band of light crossing from horizon to horizon, remember what you're seeing. You're seeing home. You're seeing the structure that contains everything you've ever known, every human who's ever lived, every story that's ever been told. You're seeing 100 billion to 400 billion stars, most invisible to your eyes, but all of them real. You're seeing a structure 100,000 light-years across, one of the largest galaxies in the universe. Genuinely enormous by any reasonable standard. And you're also seeing a structure that's tiny compared to the superclusters and cosmic filaments that make up the larger universe. Both things are true. The Milky Way is large and small, significant and insignificant, ancient and temporary. Holding that paradox in your mind, understanding that scale is relative and context-dependent, that's what it means to truly grasp the cosmic perspective. That's what it means to understand the true scale of the Milky Way in the universe. The Milky Way is vast beyond human comprehension, containing hundreds of billions of stars across 100,000 light-years of space. It's one of the largest galaxies that exist, exceptional in size compared to most galaxies in the cosmos. And yet, it's also small. a single component in structures that span hundreds of millions of light years. It's a thread in the cosmic web, one galaxy among hundreds of billions. Both perspectives are valid. Both reveal different truths about the universe and our place in it. The Milky Way is our home, and it's enormous. The universe is our context, and it's larger still. And we, tiny and brief as we are, have managed to measure both. We've mapped structures billions of times larger than ourselves. We've comprehended scales that span dozens of orders of magnitude. We've understood our place in a cosmos so vast, it challenges imagination. That's extraordinary. That's something to celebrate. That's what makes us human. Consider what this achievement means. We're made of atoms that spent billions of years cycling through stars and space. Those atoms, arranged in the complex structure of a brain, can now comprehend the cosmos that created them. The universe spent nearly 14 billion years creating the conditions for understanding to emerge. And you are that understanding. You are a way for the cosmos to know itself. The Milky Way is both large and small, significant and insignificant. And you, living in this galaxy, are both tiny and remarkable. Tiny because you're brief, small, one among billions. Remarkable because you can grasp the scale, understand your place, comprehend the vast and the ancient, despite being neither. This perspective, this understanding, changes how you see everything. Once you know you're living in a galaxy 100,000 light-years across, once you understand your atoms came from dying stars, once you grasp that you're part of a story billions of years old, you can't unknow it. That knowledge becomes part of you, and it should, because it's the truth about where you are and what you're made of. Thank you for joining me on this journey through space and scale. If you found this exploration worthwhile, a like or subscribe would help tremendously. It helps this channel reach more people who are curious about the cosmos. And remember, the next time you look up at that band of light in the sky, you're not just seeing stars. You're seeing home. One of the largest galaxies in the universe, genuinely impressively enormous, containing hundreds of billions of stars and stretching across 100,000 light-years of space. And also, when you zoom out far enough, just one galaxy among hundreds of billions, one small thread in the vast cosmic web that spans the observable universe. The Milky Way is large. The universe is larger. And you, living in this remarkable galaxy, are part of it all. Sleep well under the stars. Let's dive deeper into the diversity of stars that fill the Milky Way, because understanding this diversity is crucial to understanding the galaxy itself. We've talked about red dwarfs, yellow dwarfs like our Sun, and massive stars. But there's so much more variety than that. Between the stars, scattered throughout the galaxy, you'll find objects at every stage of stellar evolution. You'll find protostars, still collapsing from gas clouds, not yet hot enough to start fusion. You'll find T-Tauri stars, young stars still surrounded by disks of gas and dust from which planets will form. You'll find main sequence stars of every size, from the smallest red dwarfs to massive blue supergiants. You'll find subgiants, stars that have exhausted their core hydrogen and are beginning to evolve off the main sequence. You'll find red giants, stars that have swollen to enormous sizes as they burn helium in their cores. You'll find asymptotic giant branch stars, even larger, pulsating and unstable, blowing powerful stellar winds that scatter their outer layers into space. You'll find planetary nebulae, the beautiful glowing shells of gas ejected by dying stars. And, at the centers of those nebulae, white dwarfs, the hot, dense cores left behind. You'll find supernovae, massive stars in the act of exploding, and the remnants they leave behind, neutron stars and black holes. Each of these represents a different stage in the life cycle of stars. And the Milky Way contains examples of all of them, scattered across 100,000 light-years of space. The diversity is staggering. No two stars are exactly alike. They vary in mass, temperature, composition, age, rotation rate, magnetic field strength. Some stars are solitary, like our Sun. Others are in binary systems, two stars orbiting each other. Some are in triple systems, or even larger multiple star systems with 4, 5, or 6 stars, all gravitationally bound. Binary stars are actually more common than solitary stars. More than half of all stars exist in binary or multiple systems. This has implications for planetary systems. Planets in binary systems experience complex gravitational influences. They might orbit one star while the other orbits farther out, or they might orbit both stars in a circumbinary orbit. The dynamics are complicated, and it affects whether stable planetary orbits can exist. Some binary systems are so close that the stars actually touch, sharing a common envelope of gas. These contact binaries can exchange mass, with material flowing from one star to the other. In extreme cases, this mass transfer can trigger nova explosions, bright but temporary brightenings, as transferred hydrogen accumulates on a white dwarf and suddenly ignites in a runaway fusion reaction. Other binaries are wider, with the stars separated by distances comparable to planetary orbits. These systems can have planets, and we've found several examples of circumbinary planets, worlds that orbit both stars. Imagine standing on such a world, watching two suns rise and set. One might be yellow, like our Sun. The other might be orange or red, a cooler star. The sky would look alien, beautiful, nothing like Earth's single sun. Variable stars add even more diversity. These are stars whose brightness changes over time. Some variables pulsate, physically expanding and contracting in regular cycles. Cepheid variables, which we mentioned earlier, in the context of measuring distances, are pulsating stars. They swell and shrink, with periods ranging from days to months. As they pulsate, their temperature and brightness change. When they're compressed, they're hotter and brighter. When they expand, they cool and dim. This regular pulsation makes them excellent distance indicators. Other variables change brightness for different reasons. Eclipsing binaries are systems where one star passes in front of the other from our perspective, causing the total brightness to drop temporarily. Flare stars are red dwarfs that occasionally brighten dramatically in powerful flares, magnetic eruptions that release enormous amounts of energy in minutes or hours. Eruptive variables are young stars that undergo irregular brightness changes as they accrete material from surrounding disks. Cataclysmic variables are binary systems where mass transfer causes sudden outbursts. The variety is immense, and all of this diversity exists within the Milky Way. 100,000 light-years of space filled with stars at every stage of life, in every configuration imaginable. Now let's talk about star clusters, because stars don't always form in isolation. They often form in groups, and some of these groups stay together for millions or billions of years. Open clusters are loose collections of young stars, typically containing a few hundred to a few thousand stars. They form in molecular clouds when a single collapsing region fragments into multiple protostars. These stars are born together from the same cloud of gas, so they have similar ages and compositions. The Pleiades, visible to the naked eye as a tight cluster of bright stars, is an open cluster. It contains about 1,000 stars and is about 100 million years old, young by stellar standards. Open clusters don't last forever. Over hundreds of millions of years, gravitational interactions with passing stars and gas clouds gradually disperse them. The stars drift apart, eventually becoming indistinguishable from field stars, stars that aren't part of any cluster. But while they're together, open clusters are beautiful objects. Globular clusters are completely different. These are ancient, dense, spherical collections of hundreds of thousands of stars. Some contain over 1 million stars, all packed into a region just a few dozen light-years across. At the center of a globular cluster, stars are separated by light weeks instead of light years. If you lived on a planet in the core of a globular cluster, your night sky would be spectacular. Thousands of stars, brighter than Venus. No true darkness, ever. The combined light would be enough to read by, even at night. Globular clusters are old, typically 10 to 13 billion years. They formed when the galaxy was young, and they've been orbiting in the halo ever since. The Milky Way has about 150 to 200 globular clusters. They orbit the galactic center in highly elliptical paths, diving through the disk and back out into the halo. Each cluster is like a small galaxy unto itself, a self-contained system of stars bound together by gravity. Studying globular clusters tells us about the galaxy's early history. Because they're so old, they contain information about conditions in the early universe. The stars in globular clusters are metal-poor, meaning they have very few heavy elements. They formed from primordial gas that had been only slightly enriched by earlier generations of stars. This confirms our understanding of stellar evolution and chemical enrichment. The first stars had no heavy elements. They lived and died, enriching the gas. Globular clusters formed from that slightly enriched gas. Then, the galaxy's disk formed, and subsequent generations of stars became more and more enriched. The progression of metallicity from halo stars to disk stars to young stars traces the galaxy's chemical evolution over billions of years. Between all these stars, as we've mentioned, is gas and dust. But let's go deeper into what that actually means. The interstellar medium isn't uniform. It has structure, phases, complexity. In some regions, it's hot and tenuous, heated to millions of degrees by supernova explosions. This hot gas is so thin that it's almost a vacuum, containing less than 1 atom per cubic centimeter. But it's incredibly hot, glowing in X-rays. In other regions, it's warm and more dense, heated by stellar radiation. This is the warm neutral medium, containing about 0.5 atoms per cubic centimeter, still incredibly sparse by Earth standards, but dense compared to the hot phase. In molecular clouds, the densest regions, gas can reach densities of thousands or even millions of atoms per cubic centimeter. Still a better vacuum than anything we can create in a lab, but dense enough for gravity to pull it together into stars. These different phases coexist, separated by shock fronts, where gas of different temperatures and densities meet. Supernovae create bubbles of hot gas that expand into cooler surrounding gas. Stellar winds from massive stars sweep up shells of dense gas. The interstellar medium is dynamic. constantly being stirred and mixed by the energy output from stars. And throughout this medium, dust grains play a crucial role. Dust in space isn't like dust on Earth. It's not dirt or sand. It's tiny particles, incredibly small, about 1/10,000th, the width of a human hair, made of carbon or silicon compounds. These grains form in the atmospheres of cool giant stars and in the expanding shells of supernovae. They're ejected into space, where they drift through the interstellar medium. Dust grains are important because they absorb and scatter starlight. This is why we can't see across the entire galaxy in visible light. Dust blocks our view, but dust also plays a crucial role in star formation. In dense molecular clouds, dust grains provide surfaces where molecules can form. Hydrogen atoms, colliding with a dust grain, can combine to form molecular hydrogen. This is the most common molecule in the universe, and it's essential for star formation. Molecular clouds are where stars are born, and dust makes them possible. Dust also affects how we see the galaxy. It reddens starlight, scattering blue light more than red. This is why distant stars often appear redder than they actually are. The dust between us and them has scattered away the blue light, leaving the red. Astronomers have to account for this reddening when measuring distances and studying star properties. The amount of dust between us and a star can affect how bright it appears, potentially leading to incorrect distance estimates. Understanding the distribution of dust in the galaxy is crucial for understanding the galaxy's structure. Now, let's return to the question of scale one more time, because there's another way to think about the Milky Way's size that might help make it more concrete. Think about travel time. If you could travel at highway speeds, 60 miles per hour, how long would it take to cross the Milky Way? About 176 billion years. That's more than 10 times the current age of the universe. You could have started driving at the Big Bang, and you wouldn't be even close to halfway across. If you traveled at the speed of the fastest spacecraft humans have built, the Parker Solar Probe, at about 120 miles per second, it would still take about 800,000 years. Longer than our species has existed. Even at 1% the speed of light, incredibly fast by any realistic standard, crossing the galaxy would take 10 million years. There's simply no way to traverse the galaxy in a human lifetime with any technology we can currently imagine. The scale defeats us. This is why science fiction often invokes faster-than-light travel. Not because it's physically possible, but because without it, galactic civilizations are impossible. The distances are too vast. If we're limited to slower-than-light travel, we're confined to a tiny bubble around our sun. We might be able to visit nearby stars, establish colonies within a few dozen light years. But exploring the whole galaxy, visiting even a significant fraction of its stars, would take millions of years. Civilizations rise and fall in less time than that. By the time a slow spacecraft reached a distant star, the civilization that launched it might be gone. This is another aspect of the Fermi paradox. Even if intelligent life is common, even if civilizations arise frequently, the scale of the galaxy might keep them isolated. They might all be out there, scattered among the stars, each one confined to their local bubble, unable to reach each other. The galaxy would be full of isolated islands of intelligence, each one wondering if they're alone, never able to confirm that others exist because the distances are simply too vast to cross. This is what the scale of the Milky Way means in practical terms. It's not just an abstract number. It's a fundamental constraint on what's possible. It shapes what we can do, where we can go, who we might meet. The galaxy is large, and that largeness has consequences. There's one more aspect of the Milky Way we need to explore: its motion through space and its place in the larger cosmic structure. Because the galaxy isn't stationary. It's moving, falling, being pulled by gravity toward larger concentrations of mass. We've already mentioned that we're moving toward Andromeda at about 68 miles per second. But that's just one component of our motion. The Milky Way is also moving as part of the local group, and the local group is moving as part of larger structures. Our total velocity through space, measured relative to the cosmic microwave background, the ancient light from the Big Bang, is about 370 miles per second. That's over 1 million miles per hour. To put that in perspective, Earth orbits the Sun at about 67,000 miles per hour. The Sun orbits the galactic center at about 500,000 miles per hour. And the entire galaxy is moving through space at over 1 million miles per hour. All of these motions add up. You're not just rotating with Earth. You're also orbiting the Sun and orbiting the galactic center and moving through space as the galaxy falls toward larger structures. Your actual path through space is incredibly complex, a spiraling trajectory that winds through the galaxy as the galaxy itself moves through the universe. This motion is shaped by the distribution of matter around us. Gravity pulls us toward regions of higher density. The Great Attractor, a concentration of mass in the direction of the Centaurus and Hydra constellations, pulls our local group and thousands of other galaxies toward it. Beyond that, the Shapley supercluster, an enormous concentration of galaxies about 650 million light-years away, exerts its own pull. And we're part of Laniakea, that supercluster of superclusters containing about 100,000 galaxies. All of Laniakea is moving toward the Great Attractor. All the galaxies within it are falling toward the center of mass. This is what cosmic structure means in practical terms. Everything is connected through gravity. Every galaxy influences every other galaxy, at least slightly. And the large-scale structure of the universe, the distribution of galaxies across billions of light-years, shapes how everything moves. The Milky Way's path through space is determined by structures that span hundreds of millions of light-years. We're part of a cosmic dance choreographed by gravity on the largest scales. And here's something profound. All of this motion, all of this structure, all of these galaxies and superclusters, they're the result of tiny quantum fluctuations in the early universe. In the first moments after the Big Bang, space itself fluctuated at the quantum level. Some regions were slightly denser than others by incredibly small amounts. But gravity amplified those tiny differences. Denser regions pulled in more matter, becoming denser still. Less dense regions lost matter to their denser neighbors, becoming voids. Over billions of years, this process created the cosmic web we see today. Filaments and walls of galaxies separated by vast, empty voids. Superclusters containing thousands of galaxies, and galaxies like the Milky Way, each containing hundreds of billions of stars. All of it traces back to quantum fluctuations when the universe was a fraction of a second old. The scale is staggering, from quantum fluctuations smaller than an atom to structures spanning billions of light-years. From the first moments after the Big Bang to galaxies that have existed for 13 billion years. And we, living on a small planet in one of those galaxies, can trace this history. We can understand how structure formed. We can map the cosmic web. We can measure the motion of galaxies and deduced the distribution of dark matter. We've pieced together the story of how the universe evolved from a hot, dense state to the vast, structured cosmos we see today. That's extraordinary. We're part of this story, products of this cosmic evolution. And we can comprehend it. We can understand our place in it. That understanding is one of humanity's greatest achievements. Not just the ability to survive, but the ability to understand, to look at the universe and comprehend what we're seeing, to measure the Milky Way and know its scale, to grasp both how large it is and how small it is, depending on what you're comparing it to. That capacity for understanding is what makes us remarkable. Not our physical size or our longevity, but our ability to comprehend scales far beyond ourselves. And that brings us back to where we started, the true scale of the Milky Way. It's 100,000 light-years across, containing hundreds of billions of stars. It's one of the largest galaxies in the universe, exceptional by most standards. And it's tiny compared to the superclusters and cosmic filaments that span hundreds of millions of light-years. Both things are true. The Milky Way is large and small, significant and insignificant, exceptional and ordinary. Scale is relative. It depends on what you're comparing. And understanding this, truly grasping it, requires holding multiple perspectives in your mind simultaneously. From a human perspective, the Milky Way is incomprehensibly vast. From a cosmic perspective, it's one small galaxy among hundreds of billions. Both perspectives are valid. Both reveal something true about reality. And the ability to hold both in your mind at once, to appreciate the paradox without trying to resolve it, that's wisdom. That's what it means to have a cosmic perspective. It's not about abandoning your human concerns. You still have to live your life, deal with your problems, care about the people around you. But you do it with an awareness of the larger context. You know you're part of something vastly larger than yourself. You know your atoms came from stars. You know you're temporary, brief, part of a story billions of years old that will continue long after you're gone. And somehow, that knowledge doesn't make your life less meaningful. It makes it more meaningful. Because you're not just living, you're part of the universe's ongoing exploration of itself. You're how the Milky Way knows itself. How the cosmos becomes conscious of its own existence. That's profound. That's beautiful. And that's what understanding the true scale of the Milky Way gives you. Not just facts and numbers, but perspective and meaning. Let's end with one final thought about what all of this means. The Milky Way has been around for 13 billion years. It will continue to exist for billions more, eventually merging with Andromeda to create Milkomeda. And even after that merger, the stars will continue to shine. The galaxy will continue to exist in some form for trillions of years into the future. On those timescales, human civilization is a brief moment. We've existed for about 10,000 years as a civilization, a cosmic eye blink. And yet, in that brief moment, we've accomplished something remarkable. We've measured the galaxy we live in. We've understood its structure, its history, its future. We've placed ourselves within it, understood our role as temporary arrangements of matter that can nonetheless comprehend the vast and the ancient. Think about what future civilizations might think of us if they exist. Billions of years from now, when the sun is long dead and the Milky Way has merged with Andromeda, will anyone remember that we were here? Will they know that once, on a small planet orbiting an ordinary star, there was a species that looked up at the sky and understood what they were seeing? Probably not. We'll be forgotten. Our works eroded by time, our planet possibly destroyed when the sun died. But that doesn't make what we're doing now any less meaningful. Because meaning isn't about permanence. It's about the experience, the understanding, the moment of consciousness where the universe knows itself. You are that moment. Right now, reading this, understanding the scale of the Milky Way. You are the universe becoming aware of its own existence. And even if that awareness is temporary, even if it will eventually fade and be forgotten, it's still profound. It still matters. Because, for this brief moment, the cosmos is conscious. For this brief moment, atoms arranged in the form of a human brain can comprehend galaxies. That's what makes us special. Not our size or our longevity, but our awareness. Our ability to understand and appreciate the vast and the beautiful and the ancient, despite being none of those things ourselves. So, yes, the Milky Way is large. 100,000 light-years across, containing hundreds of billions of stars. One of the biggest galaxies in the universe. And yes, it's small. A tiny component of structures that span hundreds of millions of light-years. One galaxy among hundreds of billions. Both are true. And you, living in this galaxy, are both insignificant and remarkable. Insignificant in scale, remarkable in capability, small in size, vast in understanding, brief in duration, connected to the eternal through the atoms that make you up and the knowledge you can grasp. The true scale of the Milky Way isn't just measured in light years. It's measured in the contrast between the vast and the tiny, the ancient and the brief, the meaningful and the insignificant. And understanding that contrast, holding it in your mind, appreciating the paradox, that's what it means to truly understand our place in the cosmos.